Hey guys, welcome to I am for you guys. I am about to embark on something massive. 20 projects, 20 real world AI and machine learning applications from beginner to advanced, all built from scratch and explained in detail. And this is project number 1. We are building a neural network that can recognize handwritten digits with over 98% accuracy. Watch this. Boom! It just read my handwriting. And by the end of this video, you will understand exactly how AI does this. Trust me, it's way simpler than you think. This is just the beginning of our 20 project journey. Each week we are building something more advanced, more exciting, more mind blowing. So if you want to master AI or ML with me, hit the subscribe button right now and turn on notifications. Alright, let's kick off project 1. Smash that like button and let's dive in. Some people write their sevens with a line through them, some doesn't. Some ones are straight, some are curvy. Our neural networks needs to handle all of these. Alright, let's code. Open up your Python environment. I am using VS Code, but use whatever you are comfortable with. Okay, let me import necessary libraries and let me break down this real quick. NumPy for number crunching and operations, matplotlib to visualize our digits, and the TensorFlow or Keras, the powerhouse for building our neural networks. Don't have this installed? Pause this video and run pip install TensorFlow NumPy matplotlib. I'll wait. Done. Great. Let's move on. Now load the data. We have to load and pre-process MNIST data. X underscore train comma y underscore train again x underscore test comma y underscore test MNIST dot load underscore data. See, this one line does something incredible. It downloads 70,000 handwritten digits images automatically. How cool is this? We get 4 things here. X train 60,000 training images. This teach our model. And Y train labels for those images, what digit they actually are. X test 10,000 test images to check how smart our model got. Y test labels for test images. Now we have to do data pre-processing. Before we feed this to our neural network, we need to do some pre-processing. Think of it like preparing ingredient before cooking, like x underscore train dot reshape of x underscore train dot shape of comma 28 comma 28 comma 1 dot as type of float 32 by 255. The same way we have to do for test also. That means we can copy this and we can paste here and just need to change x underscore test and here also x underscore test. Enough. Here 3 things happening here. Let me zoom in. The first one is reshape. We are adding an extra dimensions. Why? Because our CNN expects a channel dimension. For grayscale image we will add 1. For color images we will add 3. And one more is like converting to float. Neural network works better with decimal numbers, so we convert from integer to float. And the final one is normalizing. This is a crucial. We divided by 255 to squeeze all pixel values between 0 to 1 And why? Because neural networks learn faster with the smaller numbers. It's like, would you rather calculate with 1 lakh or with 1? Exactly. Next one is the labels. Y underscore train equal to 2 underscore categorical of y underscore train comma 10, and y underscore test equal to 2 underscore categorical of y underscore test comma 10. This converts our labels into one hot encoding. Instead of just saying 7, we can create an array of 10 numbers where only the 7th position is 1. See, now label like 7 and before also like 7. Now after like 0 0 comma 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 0. Think 1 2 3 4 5 6 7, but here index will start from 0, it will come to here, like this position is the 7th position. Why? Because our neural network output probabilities for each digit. This format makes training way more efficient. Like this it will train our model. Now building the neural network. Now for the exciting part, build our brain. Like we are using a CNN. Conventional neural network, don't let the fancy name scare you. Like model equal to sequential of like enter con 2D of 32 comma kernel underscore size equal to 3 comma 3 comma activation equal to relu comma input underscore shape equal to 28 comma 28 comma 1. Then max polling 2D like pool underscore size equal to 2 comma 2, and then dropout of 0.25 comma flatten and flatten, that's it, and come to dense of 128 comma activation relu, and the dropout again like 0.5, and again tens of 10 comma activation same soft max. Then that's it. Let me walk you through each layer. Think of it's a building a tower. Like first one is conventional layer, like conv 2D of 32 canal size 3 by 3 activation relu input shape 28 by 28 comma 1. This is our future detector. Imagine you have a tiny 3 by 3 magnifying glass sliding across images. It looks for patterns, edges, curves, lines. We have 32 of these magnifying glasses, each looking for a different features. Relu activation. It's simple. If a number is negative, it make it 0. If positive, it keep it. Like this helps our network learn faster. The second layer is like max pooling.
Like pooling is like downsampling. We take a 2 by 2 section and keep only the maximum value. Why means like if we have like p4 2 comma 3 or like 1 or 4, after it will be like only 4. It reduces the image size, makes training faster, and helps our model focus on important features like while ignoring noise. The other one is dropout. This is brilliant. During training, we randomly turn off 25% of neurons. Sounds crazy, right? But here is the genius. It prevents outfitting. It's like studying with random pages missing. You learn the concept, not just memorize the book. Okay, the next one is flatten. Time to flatten. We take our 2D features, maps, stretch them into one long line of numbers. Why? Because our next layer need to be 1D input. That means our dense layer like hidden layer. We can call it as hidden layer. Now we have 128 neurons fully connected. Each neuron layer looks at all the features and makes decision. Think of it as 128 experts voting on what digit they see. Another dropout, more dropout, this time 50%. We are getting serious about preventing outfitting. The last one is output layer like dense again. This final layer 10 neurons own one for each digit like 0 to 9. Softmax activation converts the outputs into probabilities that sum of 100%. Example like digit like 0 means 2%, or I like again digit 1 it will like 1%. Again if digit 2 it's like 3%. Again digit 3, this is will give 85 89%. This is the winner. Like it will point out, like it will see like which one is the best one, like maybe this one is the best one, or else it will check again 4. If this is like 4%, it won't take. If you go for 5, 6%, like on keep on. The main winner is this one, because this is the good probability of digit to finding this. The highest probability wins. That's our prediction. The next step is compiling the model. The model dot compile of loose function we have to write like categorical underscore cross centropy and optimizer Jadia I think equal to Adam. The next one is metrics, and this accuracy. See, model there are three critical components here, like loose functioning, like this measures how wrong our predictions are. Lower is better for multi-class problems like ours. This is the GLAN standard. The optimizer, this is the next one, is Adam optimizer. Adam is like a GPS for our neural networks. It figures out the best way to adjust weights to minimize the loss. It's smart, it's fast, and it's adaptive. The last one is accuracy. This is accuracy metrics. Simple, what percentage did we get right? This is what we care about. Now it is training time. Like model dot fit x underscore train comma y underscore train comma patch underscore size equal to 128 comma epochs like 10 epochs. We will go for 10 epochs. Validation data like x underscore train comma y underscore train. Let me explain what happening. Like here the batch size is 128 and epochs, this batch size, what we will do, we don't show all 60,000 images at once, we show 128 at a time. Update waits, then show the next 128 like epochs 10. This is like here we go through the entire dataset like 10 times we will go. Each pass our model gets smarter. The validation data is like after each epoch we test one image the model has never seen. This tells us if we are actually learning or just memorizing. Now we'll check once how our application is working, like python MNIST dot digitreader.py. See, we are getting one issue like trace most calls lost relay activation. The line number 19. Okay, kernel NEL is sorry guys, this is KENEL size activation relu input side, everything is looks good. We'll run again. See epochs now it is showing here accuracy. We are checking our accuracy, it is hitting already 81%, 82%. See accuracy how much we are getting. Epochs 1 is done, we got accuracy like 90%, we lose 33%, value accuracy 97%, value loss only 1% per. See, this is our accuracy. This is where our model is working like good with good accuracy. That's insane for such a simple model. See, everything we are hitting like 96%, 95%, 90%. It will run, it will take some time. See, overall we hit it 98%. Now we'll go for the next like evaluation. Here test underscore loss comma test underscore accuracy equal to model dot evaluation of x underscore test comma y underscore test comma verbose 0, and we'll try to print this like f codes test loss test underscore loss colon dot 4 f codes. Oh sorry, codes we didn't give properly here. Now it's proper I think, but this should be outside this. Again we'll print one more time f codes test accuracy like test underscore accuracy colon dot 4f. Now we'll again run this, we'll see the result. See, Now it's running epoxes again. Now we'll see this. Once after the epoxes runs, we can see the prints. See, our test loss is 0.0366. Our test x 1880 correct. That's only 122 is not correct, like mistakes. For context, humans are around 97 to 98 on this dataset because some digits are genuinely ambiguous. Okay. Okay. Next, saving this model. We have to say like model dot save of MNIST. Will give MNIST model dot h5. Okay, that model where we are saving like MNIST dot underscore model dot h5. We share our trained model, so we don't have to train it again. This file contains all the learned weights, years of visual experience in one file, like making predictions. Let's see our model in action. Like idx equal to np dot random dot randint array n randint of 0 comma x underscore test dot shape of 0. Sample, will keep it like sample image x underscore test of idx dot reshape of 28 by 28. Now plt will call matplotlib imshow of sample underscore image comma cmap equal to gray. Then plt dot title of will show sample test image, like plt dot show bracket. Again this will show random digits. Again prediction equal to will call model dot predict of x underscore test of idx dot reshape of 1 comma 28 comma 28 comma 1. Prediction underscore label, we will take np dot argmax of prediction. Again now we'll print this of f quotes predicted digit add check prediction label. That's it. Now we'll see the prediction again. Now this will print. Oh, we got an error by saying random. Okay, random, I gave a random randit. It's correct now. We'll again rerun this. After issue fix, again epoch is running, last one is running. Now see, predicted digit 4. It's telling that cannot show the PLT slow warning. It is giving, it gave predicted digit 4. Like this matplotlib we gave 4 randomly and it decided 4. Looks at this, our model is confident, it is saying 4 and it is right. Amazing, it's getting them all correct. Our model is ready. But wait, we aren't done. I built a web app where you can draw digits and see predictions in real time. I'll draw a messy 3. See, if you check, this is our web application which I developed, and I have added our model into this, and by using this I created backend code with Flask. To that I called a API in frontend. Overall it's running on port 5173. See, I'll try 3 messy 3. See, this is the 3. Now our prediction is correct or not, we'll check. Boom, prediction is correct. See, our model is working fine. Now I'll write 5. See, 5 came. If I write 4, it came correctly. If I write 6 correctly. 96% accuracy, it is giving confidence level. Nailed it. This is using the exact same model we just trained. I used Flask for the backend and React for the frontend. I'll link the full code in the description. Let's recap what we learned today. What CNNs are: specialized neural networks for image recognition, how convolution works, sliding filters, detecting features, and pooling means reduces size and focuses on important features. Dropout prevents outfitting by random deactivation. Data preprocessing normalized and reshaped for better training, and training process batch processing over multiple epochs. Most importantly, you just build an AI that can see. That's incredible. That is project number 1 of 20. We just build an AI that can see and understand handwritten digits. How cool is that? If you enjoyed this first project and want to join me on this epic 20 project AI or ML journey, smash that like button, hit subscribe and ring that notification bell so you don't miss project number 2. Full code, datasets and all resources are linked in the description. Got questions about this project or suggestions for future ones? Drop them in the comments. I'll read every single one and I'll respond. Thank you for being part of project 1. I'll see you in the next week for the project 2. Until then, keep coding, keep learning and stay curious.